Here are a couple of things that we've worked with before, the golden rectangle and the Fibonacci sequence, and these two items right here are going to allow us to simplify this new expression, which is called a continued fraction. This continued fraction starts like this: 1 plus 1 over 1 plus 1 over 1 plus 1 over so on and so forth, on down like that. It continues an infinite number of levels down. So the problem with it is there's no way to get down to the bottom to work our way back up to simplify this. But if we use what we know about the golden rectangle and the Fibonacci sequence and look at this in stages, we'll be able to simplify it. So I'm going to stop for a second and put some things on the board and then come right back. Hang on. Okay, so I've written these things over here on the board, and so what I want to do is just kind of take it stage by stage and see if I can notice a pattern to this. So first I've written 1 plus 1 over 1 plus 1. That's one level. Now over here I have two levels, then down 3 levels, down 4 levels, and if we notice a pattern there, we may be able to decide what this continued fraction is actually equal to. So let's simplify. Here I have 1 plus 1 over 1 plus 1. That's 1 plus 1 half. That's 2 halves plus 1 half, which is going to be 3 halves. Okay, so that's my answer right there to this first expression. Now when I look at my second expression, I see that down here in the denominator, this is what I just simplified. That is 1 plus 1 over 1 plus 1. So that's this expression. So I'm going to take the results of my previous work and write this as 1 plus 1 over 3 halves. Okay, so this I know comes out to be 3 halves because of what I did right here. Now the reciprocal of 3 halves is 2/3. So this is 1 plus 2/3. That's 3/3 plus 2/3, which is going to give me 5/3. Now I go to my next problem right here, and I notice that this part is exactly the same as what I did just here. Just right here. So what I'm going to do is take what I've already done and substitute it in, and I get 1 plus 1 over 5/3. That will be 1 plus the reciprocal of 5/3 is 3/5, and then 5/5 plus 3/5 will be 8/5. Now, do you see a pattern in these fractions right here? If you look back to the Fibonacci sequence, you see that this is 3 halves, this is 5/3, this one is 8/5. So if I was to go one more number in the Fibonacci sequence, I know that would be 13. And using my inductive reasoning, I would say, well, this one, if it follows this pattern, is going to come out to be 13/8. And in fact, that's exactly what happens. This comes out to be 13/8. You can simplify this if you want to, but that's what you get. So as we travel down this sequence right here, we see we get ratios of consecutive Fibonacci numbers. Now the next thing I want to do is take each of these fractions and convert it to a decimal. So when I do that, when I convert to a decimal, this turns out to be 1.5. 5/3, when I divide 3 into 5 or do it on a calculator, I end up with 1.6, so on and so forth. It just keeps going with 6's there. 8/5 turns out to be 1.6, and then 13/8 will turn out to be 1.625. So what's happening right here is that it looks like it's going towards 1.6 something. That 6 is kind of stabilized. If we could go further on down this sequence of ratios of consecutive members of the Fibonacci sequence, we might get a better idea of where this is going. So I'm going to erase some of this, come back, and we'll see what we have. Okay, so what I've done is erase what I had before, and I've extended the Fibonacci sequence. Here we have 8, then 13, 21, 34, 55, so on and so forth. Here's what I had with the results of the little calculations I was doing. 3 halves is 1.5, 5/3, 8/5, 13/8. Now if I go to the next one, it's going to be 21 divided by 13, these two consecutive members of the Fibonacci sequence. If I do that as a decimal, it comes out 1.615. Then 34 over 21, that's 1.619. 55 over 34, that one is going to be 1.618, and then from there on it stays at 1.618. So it looks as if this sequence of consecutive ratios of consecutive members of the Fibonacci sequence is actually traveling towards the golden ratio over here. And in fact, that turns out to be true. So we can say that this expression right here is actually equal to 1 plus square root 5 all divided by 2. Now that's a conjecture that we're making based on this inductive reasoning that we're doing right here. I'm going to go to the next board and give you a little deductive proof that that is actually in fact true. Okay, so here I have the continued fraction 1 plus 1 over 1 plus 1 over 1 plus 1 over so on and so forth. It goes infinitely far down like this. Now if I can say let's let x be equal to whatever this continued fraction comes out to be, we'll just say let x be equal to the continued fraction, then it must be true that x is equal to 1 plus 1 over x, because of the property that infinity has, that we can add another level to any time we want. It won't change it. It's already all the way on out there. So if I look at this continued fraction, that's the continued fraction right there. But if I just look at this part of it right here, that's the continued fraction also. Both of them go infinitely many levels down. So if I say x is equal to the continued fraction, then x must be equal to 1 plus 1 over, that's x also. So if you can get that part of it, the rest of it's very easy. I'll just take this equation right here and multiply both sides by x. I'll end up with x squared is equal to x plus 1. Quadratic equation, I'll put it in standard form. X squared minus x minus 1 equals 0 when I add the opposite of those two terms to both sides. Now here I'll use my quadratic formula, so I'm going to say this. X is equal to negative b, which is negative 1, plus or minus square root of b squared, negative 1, quantity squared, minus 4 times a times c, all divided by 2 times a. So negative b plus or minus square root b squared minus 4ac all over 2a. Well, what is this going to simplify to? Let's take it right up here. And I'll have the opposite of negative 1, that's just going to be 1, plus or minus, but look, this is all just a string of positive terms right here, so it's not going to be 1 minus something, it's going to be 1 plus something. So I'm just going to drop off the minus sign. 1 plus square root of negative 1 squared is 1 minus 4 times 1 times negative 1. Well, negative 4 times 1 times negative 1 is positive 4, plus positive 1 is going to be 5, all divided by 2 times 1, which is 2. Okay, so there you have it. In fact, that if x is equal to this continued fraction right here, then x must be 1 plus 1 over x. And if I simply solve that equation, use the quadratic formula, what drops out? The golden ratio. So in fact, that continued fraction is equal to the golden ratio. Now, for those of you in a calculus class, go to one more board and show you a couple more things. Okay, if you're taking a calculus class, just to add a couple things here, just a little notation, but if I take the Fibonacci sequence, it looks like this, and I say I'm going to let f sub n represent the nth term of the Fibonacci sequence, then that whole string of little ratios that I just had that seem to point to the golden ratio, all that work can be written like this. The limit as n goes to infinity of f sub n plus 1 over f sub n, that just stands for a ratio of consecutive members of the Fibonacci sequence. The limit as n goes to infinity of this is 1 plus square root 5 over 2. So I know if you're a calculus student, you probably had the feeling that what we were working with was limits right there, and in fact that's exactly what we're doing. So all you have to do is write down the general term of the Fibonacci sequence as f sub n, then here's your ratios, and what we're doing is looking what happens as those ratios get farther and farther along in the Fibonacci sequence. And sure enough, with that little deductive proof we just did, we've showed that the limit as n goes to infinity of this ratio must be 1 plus square root 5 over 2. So just a little notation to go with this problem in case you're in a calculus class.